All over Europe, climate change is a growing concern, with global sea levels rising between 16 and 20 centimetres since 1900. Climate change is undeniably having an effect on oceans, land surfaces, ice caps and weather patterns across the globe. It is well understood that climate change is caused by atmospheric gases such as carbon dioxide and methane. When we look at these trace gases, there is an obvious correlation between human activity and climate change.
What you see here on this graph is the CO2 concentrations of the atmosphere over the last 800,000 years. And you see that these values are going up and down in different phases. You see on the blue lines here are indicating ice ages, and the orange lines here are indicating periods between ice ages or periods where it's much warmer. But you also see that over the last 800,000 years, the value was always below 300 parts per million, and suddenly, since the last century, it goes up very steep towards 400 parts per million or even beyond. And this is what we have today. This is the increase of carbon dioxide drastically increasing over the last 100 years caused by human beings.
In order to tackle climate change, scientists and governments need reliable data to understand how our planet is changing. This can be provided by ESA, which monitors our planet from space. With 4 EU Copernicus Sentinel missions and 4 Earth Explorer missions in orbit, ice thickness and coverage, deforestation, soil moisture, sea level and ocean surface temperature, as well as other essential climate variables can be measured. These satellites have global coverage, revisiting the same region every few days, therefore providing a good understanding of the health and behaviour of our planet and how it's affected by climate change. In turn, this offers decision makers key information for mitigating strategies and policies.
Frequency and consistent observations of our environment are very important if we want to give decision makers the key into their hand on where humankind has to change practices, where we have to be mitigating for encroaching impacts on our environment.
Satellites can show us how the world has changed. Like here in the Camargue, France, where the coastline has retreated more than 200 metres in the last 20 years. In the 1980s, seawalls were constructed here in a failed attempt to stop the rising water. Back then, sea level was rising, but more slowly than it is now. Over the last 5 years, records show that the rise in sea level is accelerating. Soon part of this delta will be lost to the sea. And what is happening here is happening in many parts of the globe. Worldwide, more than 370 million people live less than 5 meters above sea level. Over 100 megacities such as New York or Tokyo are near the water. All are at risk. Satellite data gives us the facts so that we can prepare ourselves for the rising tide and protect coastline populations. This data is also used in ESA's Climate Change Initiative, where ESA scientists preserve and work with long-term data sets going back to 30 years and more to get an even better understanding of climate change. Thanks to satellites, we have evidence that the planet is in danger. Now it is up to people on Earth to take the necessary measures in time. The key for sustaining life on Earth might come from space.
Dragon Endurance cruise ship, moving Rubio's seat liner from the Roscosmos Soyuz MS-22 spacecraft to the Crew Dragon. The seat liner move is taking place following the external cooling loop leak on Soyuz last month. This move ensures that Rubio would be able to return to Earth aboard Crew Dragon and reduces the heat load inside the MS-22 spacecraft for cosmonauts Sergei Prokopyev and Dmitry Petelin in the unlikely event of an emergency evacuation from the space station. A replacement spacecraft, Soyuz MS-23, will launch to the station next month. Once docked to the station, Prokopyev, Petelin, and Rubio will return to Earth on that Soyuz later this year. And that's Space to Ground for this week. Thanks so much for watching. You can get a daily on-orbit status report by visiting our space station blog at blogs.nasa.gov. We'll see you next week.
One of the great powers of the International Space Station is its duration. The ability to do an experiment, take that knowledge, design a new experiment, follow on with that knowledge, and then do the next generation after that.
NASA's been launching vehicles for decades, and each one of those vehicles has an experiment on them. But never before have we had a laboratory totally dedicated to these kind of experiments.
One of the things that's most promising is that the scientific value and the economic value that will come from the space station research is just starting to show up.
The developments that we're making now are really setting the stage for this commercial market in this space. The efforts that have led up to this through the performance of all of these research investigations that we've already had on board, doing foundational research and testing out new technologies and methods, feed this market and feed the capability of doing future research in space and also in having new commercial entities operate in that space.
We put together the ISS Benefits for Humanity book to really compile the stories that we knew of the amazing things that had been accomplished. The challenge with science is that it takes time. So even a new discovery that is clearly relevant to treating a medical condition could take decades for that treatment to actually come to market. And so we wanted to capture the state of those different new discoveries and how they were proceeding into benefits for humanity.
But we also wanted to tell the stories of the people whose lives had already been changed.
We've put in specialized sections to both economic value and scientific value in order to try and demonstrate to folks what sort of value space station research has.
So we wanted to capture
the scientific valuation section. We were interested in just saying, hey, we have all these publications, these scientific publications that come from ISS. What should we do with them? How should we communicate why they're important? Yeah, we've got thousands of publications, but what does it mean? And how has it advanced science as a whole for Earth and also for spaceflight? So what was shocking to me is, wow, look at all the publications that have come from space station research.
And other people in non-space disciplines are finding those publications and using them in their own research. And where you can integrate space research into everyday research on Earth, you know you're having the most impact on science.
One thing we're adding is a lot more information about commercial development in low Earth orbit
that is leveraging the space station.
The space economy today is still emerging, but its valuation has doubled in the last 10 years, and there are more active participants in low Earth orbit than there have ever been. The International Space Station has contributed to the commercialization in a couple of different ways. First, with the commercial resupply, encouraging companies to develop their own capabilities, and then those capabilities can be used not just by the International Space Station. In terms of research, there are 12 commercial facilities that are operating right now, and they've greatly expanded the kinds of research that can be accomplished on ISS, and they're really bringing both new customers into the space market, but also they are allowing new entities to form that are learning the processes by which you conduct business in space.
Commercialization is key to the further exploration mission that NASA has. We intend to use Space Station to help commercial entities enter the market in low Earth orbit. And we also expect them to be able to provide goods and services that someday will help us in our exploration mission beyond low Earth orbit.
Scientists tend to ask, what's the next question? So the next question for Space Station is, what are we going to do next with this platform?
This is the golden age of research. We will likely never see such a strong microgravity science program in the future. We will have lots of human exploration, but to have a sustained laboratory in the way that we have now's the time.
This research is feeding our exploration goals beyond low Earth orbit and developing the companies that hope to make low Earth orbit part of their business plans. These two goals go hand in hand, and the International Space Station is the way to get there.
We really want to tell the stories of people and products and economic development, all of those things that are making the world a better place through our international cooperation on the space station.
Most of the children, they come here with waterborne disease.
So many children under 5 suffer from diarrhea.
They're complaining about the abdominal pain, skin rashes.
They get waterborne illness through drinking water.
Most of the community members had little knowledge regarding the use of safe water and what safe water is.
Because most of the water we use it without knowing it is affected with disease or not.
So we need to test them so that we make sure that the water is safe or not safe.
A lot of people have the idea that water quality is too hard to do in the field and it's too complicated.
Having to transport samples, having to have reliable electricity, having to heat samples or keep samples at certain temperatures or put them in refrigerators.
But probably the biggest challenge is actually the cost.
The price was really high, up to $300 a test.
So all those things come together to make it really difficult to use a traditional laboratory approach when you're testing water. What's been missing is the really simple, cheap test kit, and that solution came from above. On the space station, we recycle almost all the water that the astronauts drink, and that constitutes a risk because if that water became contaminated, the astronauts would have to abandon the space station in the worst case scenario. What we needed on the space station was something that was small, easy to transport, and didn't require a lot of training for the astronauts. We developed a water test kit that was really easy to use and used off-the-shelf components, and we called that the Microbial Water Analysis Kit, or MWAC. It's basically a bag that changes color in it, and the astronauts just had to hook it up to the water system, take the sample, store it overnight, and read it the next day. It worked great, and it's still in use today. This was when we realized we had a chance to make a difference in the world using the same technology that was used by NASA, but applied in a remote area of a developing country.
We started MWater for the biggest health crisis on the planet, which is a lack of safe water. The test kit is revolutionary because of its cost. It lowers the cost of testing water points from hundreds of dollars to about $5 to $7. It can be done on site in the remote region, and it can give you a result within 24 hours.
I take a sample today, tomorrow I have results. To use a water kit is very easy.
But we learned that testing water by itself wasn't enough. With the mobile app, people could map water sources and record the data.
So that way we're building sort of a global database of water information that everybody can contribute to and share with others.
So what that meant was people who before didn't have a feasible and affordable way to test water suddenly had the means to know which water sources around them were safe.
It's made people much more aware of the issues of water quality. That's a very powerful thing.
And that's all due to technology that we've borrowed from the International Space Station. So now we're able to assemble a really low-cost water quality test kit to ship all over the world.
We've been working with the local health ministry and the water utility in Mwanza, Tanzania since 2013.
Through that technology, most of the citizens in Mwanza have an increased awareness regarding the kind of water they use and whether it causes them any waterborne illnesses or not.
People are now treating their water and avoiding sources of water which could be contaminated. I've seen a growing awareness.
It is very unusual for technology that is used in international space stations to be used in developing countries like Tanzania, but it can be used and it should be used because this technology is not limited to only developed countries but for all humankind.
The International Space Station is the most unique laboratory that exists. There are things that you can learn, things that you can do in space that you just can't do on the Earth.
Space Station really provides an opportunity to explore, for example, say medical applications.
The aging and the osteoporosis and muscle wasting conditions are greatly accelerated in microgravity.
Understanding those phenomena allow us to look at how we can improve treatment of disease here on Earth.
What we have is the capability to affect people's quality of life.
But it's not just drug companies that can benefit from experiments or research in space, but it's a host of industries across the board.
But it wasn't always easy to get there.
Historically, access to space was limited to companies and corporations which were selected by the government, and what we lost was the true creativity of so many innovative smaller companies that really didn't understand how to get to space.
When we were doing the reauthorization of NASA, we wanted to expand the opportunities to different areas of experimentation and also different entities.
Recognizing the untapped potential for commercial access to space, in 2005, Congress declared the U.S. portion of the International Space Station a national laboratory.
Essentially, it opened up opportunities for research that could be done on the space station that would benefit us here on Earth.
Everyday companies and everyday researchers and everyday people can think about using the space station. That's a fundamental change that was never allowed before.
Today, we offer opportunities to the researcher that never existed before.
Whether it be seed funding to help support the actual project,
to access to experts to create hardware,
that rocket ride up, the on-station time with the astronaut as your lab technician. What we're doing is really making it as easy as possible for people here on Earth to do space-based research without becoming space experts.
Our part of the mission is to help guide these non-traditional, innovative users from their traditional labs here on the ground to a very unusual and important asset in space. The ISS National Lab has space versions of hardware that you can often find in laboratories here on the ground.
Everything from even animal habitats,
plant growth chambers,
freezers,
3D printers,
Earth observation windows,
incubators,
furnaces,
the centrifuges,
microscopes.
The list goes on and on. So we're working with companies that you would never imagine, and they would never have imagined using the International Space Station, and they're seeing great results from that.
And the International Space Station offers researchers like me an opportunity to find the key variables.
It's helping us to pinpoint therapeutic molecules.
The space station really provides us a unique opportunity, a unique environment to do some basic and fundamental research that allows us to develop products better.
The ISS allows us to do a series of experiments in weightlessness that will have profound impacts for life on Earth.
Having a U.S. national lab in space has allowed for the formation of a wide range of companies. It's creating a new economy, a sustainable marketplace that has services, commercial products, competition. There's no limit to what we can be doing in a few years.
One of the great powers of the International Space Station is its duration. The ability to do an experiment, take that knowledge, design a new experiment, follow on with that knowledge, and then do the next generation after that.
NASA's been launching vehicles for decades, and each one of those vehicles has an experiment on them. But never before have we had a laboratory totally dedicated to these kind of experiments.
One of the things that's most promising is that the scientific value and the economic value that will come from the space station research is just starting to show up.
The developments that we're making now are really setting the stage for this commercial market in space. The efforts that have led up to this through the performance of all of these research investigations that we've already had on board, doing foundational research and testing out new technologies and methods, feed this market and feed the capability of doing future research in space and also in having new commercial entities operate in that space.
We put together the ISS Benefits for Humanity book to really compile the stories that we knew of the amazing things that had been accomplished. The challenge with science is that it takes time. So even a new discovery that is clearly relevant to treating a medical condition could take decades for that treatment to actually come to market. And so we wanted to capture the state of those different new discoveries and how they were proceeding into benefits for humanity. But we also wanted to tell the stories of the people whose lives had already been changed.
We've put in specialized sections to both economic value and scientific value in order to try and demonstrate to folks what sort of value space station research has.
The scientific valuation section, we were interested in just saying, hey, we have all these publications, these scientific publications that come from ISS. What should we do with them? How should we communicate why they're important? Yeah, we've got thousands of publications, but what does it mean? And how has it advanced science as a whole for Earth and also for spaceflight? So what was shocking to me is, wow, look at all the publications that have come from space station research, and other people in non-space disciplines are finding those publications and using them in their own research. And where you can integrate space research into everyday research on Earth, you know you're having the most impact on science.
One thing we're adding is a lot more information about commercial development in low Earth orbit that is leveraging the space station.
The space economy today is still emerging, but its valuation has doubled in the last 10 years, and there are more active participants in low Earth orbit than there have ever been. The International Space Station has contributed to the commercialization in a couple of different ways. First, with the commercial resupply, encouraging companies to develop their own capabilities, and then those capabilities can be used not just by the International Space Station. In terms of research, there are 12 commercial facilities that are operating right now, and they've greatly expanded the kinds of research that can be accomplished on ISS, and they're really bringing both new customers into the space market, but also they are allowing new entities to form that are learning the processes by which you conduct business in space.
Commercialization is key to the further exploration mission that NASA has. We intend to use space station to help commercial entities enter the market in low Earth orbit. And we also expect them to be able to provide goods and services that someday will help us in our exploration mission beyond low Earth orbit.
Scientists tend to ask, what's the next question? So the next question for space station is, what are we going to do next with this platform?
This is the golden age of research. We will likely never see such a strong microgravity science program in the future. We will have lots of human exploration, but to have a sustained laboratory in the way that we have now, now's the time.
This research is feeding our exploration goals beyond low Earth orbit and developing the companies that hope to make low Earth orbit part of their business plans. These two goals go hand in hand, and the International Space Station is the way to get there.
We really want to tell the stories of people and products and economic development, all of those things that are making the world a better place through our international cooperation on the space station.
1988, Dr. James Hansen, then director of NASA's Goddard Institute for Space Studies, stood before the U.S. Senate and testified that
global warming has reached a level such that we can ascribe with a high degree of confidence a cause and effect relationship between the greenhouse effect and observed warming. It is already happening now. This last year, 2021, comes in as the 6th warmest year on record, and it continues this large, long-term warming that Jim Hansen was detecting even in 1988. And in 1988, that was also a globally warmest year, but now that ranks only 28th in the ranking. And so the warming that we've had since Jim Hansen's testimony has been dramatic and totally vindicates the concern and the warnings that he put out at that time.
the Goddard Institute for Space Studies, or GISS for short, maintains NASA's record of Earth's surface temperature, called GISS-Temp, that shows a clear and unequivocal increase in our planet's temperature. GISS-Temp stretches from 1880, long before NASA existed, until the present day. Now, when you think of NASA, you probably think of, well, space, right? And we do lots of work studying Earth from above. But the GISS-Temp record is actually built from the ground up. We collect measurements taken from weather stations, Antarctic research stations, and ships and ocean buoys all around the planet to understand what temperature changes look like globally. And why does the record start in 1880? That's the earliest period that we have sufficiently reliable measurements from ships and weather stations in enough places to be confident in the global record. Interestingly, it's also shortly after the time we call the Industrial Revolution, when humans started putting significant amounts of carbon dioxide in the atmosphere. But we'll get back to that later.
There are millions of measurements over the last 140 odd years. We put those together. We're using data from literally tens of thousands of different stations around the world. We use the information that's there to create a global picture of what's happening, and that gives us a very accurate estimate of how any year ranks, or what the anomaly is for any one year compared to what happened in the 19th century or what happened in the middle of the 20th century.
So we have our statistical reconstruction of Earth's recent climate, but in research science we like to check our work. There are a couple ways we can do this. First of all, teamwork. Our colleagues at NOAA and at other agencies and universities around the world also create their own records, and we can line them up side by side and see just how closely they align. Everyone's independent climate records show the same thing. Earth is warming significantly and rapidly. And here at NASA, we have an even cooler way to check our work. Space. Right now, we have more than 24 satellites dedicated just to studying our planet. Satellites can take measurements of the entire planet and line them up with our estimate of global temperature change. And sure enough, they also match. Our measurements from space match up well with what our analysis tells us. Earth's climate is warming. The next big question: why is our planet warming? Well, let's jump back to the Industrial Revolution. The release of carbon, mostly carbon dioxide, from human activities like driving cars, flying planes, and industrial burning of fossil fuels is responsible for the majority of climate change. Carbon exists in stores underground as oil, gas, and coal. When we burn it, we release it into our atmosphere, where it traps excess heat coming from the sun, raising the temperature. We've known for more than a century that carbon dioxide added to our atmosphere traps additional heat and is a major contributor to the greenhouse effect. So we can also track the concentration of carbon dioxide in our atmosphere, the primary cause of the current climate change. Both from space, using NASA satellites like the orbiting Carbon Observatories 2 and 3, and from the ground. If you've heard of the Keeling curve, you're familiar with one of these records. Researchers have been taking daily measurements of atmospheric carbon dioxide from Mauna Loa, Hawaii since the 1950s. From space and the ground, the signal is clear. There's a lot more carbon in the atmosphere than there used to be. Other things have changed too. We've chopped down tropical forests, caused the ozone hole, and filled the air with soot, smog, and other kinds of air pollution. And this is on top of natural variations caused by the dynamics of the ocean, or volcanoes, or variations in the sun's activity. And so we can ask whether it's human activities warming our planet. At NASA, we have some big and powerful computers, able to make 6.8 trillion calculations per second. We put these huge supercomputers to work to recreate Earth's climate. So we have thousands of ideas of what could naturally cause climate change. We have 4 billion years of history where nearly anything and everything you could imagine has impacted Earth's climate. But each of these events has their own distinct fingerprint, which we can identify, a pattern of behavior with natural variability. Using supercomputers, we can run simulations of natural climate drivers, solar energy changes, wobbles in Earth's orbits, ocean turnover, volcanic eruptions, and we can run simulations of human effects. And what we've seen is...
It's us. There's no way around it. Looking at the evidence, we're the force that's enacting these changes. I'm so proud of our ability to understand the climate, but I'm terrified of what we found.
But it's not just the causes of climate change, it's also the effects. Because it's not just about knowing why our planet is warming. It's also about understanding and preparing for the effects of added warmth.
Measurement of global average temperatures is so important because it's one of the most direct indicators of Earth's changing climate. But the Earth is really a system of environmental systems: land, ocean, atmosphere, and ice. And changes in one system impact the others. Our oceans are our first line of defense in climate change because they absorb so much of the extra trapped energy in the Earth system.
We are seeing the impacts of climate change now. Now we know that as our climate warms, wet areas are getting wetter and dry areas are getting drier. For example, we see more intense snowstorms. We see slower hurricanes that are causing more precipitation that inundate land. And we have more extreme precipitation in the form of atmospheric rivers that come from the Pacific and reach our west coast.
The oceans are absorbing a large amount of heat because of climate change. And once that heat is in the ocean, it actually travels all around the planet because of the ocean currents. And that has impacts on local weather and long-term climate.
As the planet warms, it's not just the ocean that's warming, it's also the ice that sits in the ocean and on land. The ice on land being warmed increases melting, which is increasing freshwater input into the polar oceans and causing sea levels to rise across the globe.
So as the climate is changing, we really are seeing a lot of changes to the environment up in the Arctic. We're seeing more permafrost thaw when it's warmer up there. The warmer air temperature can lead to warmer ground temperature, and we get that thawing of that permafrost layer.
We're finding that the fire season is being exacerbated by longer periods of drought and decreased snowfall.
Knowing that our climate is changing due to human activities means that we know how to lessen the effects of future warming. And knowing how we know what causes climate change confirms that our efforts would be meaningful. The situation is serious, but it's not hopeless. Together, we can decide to make a better choice.
We're never going to stop exploring the unknown in air and space. We're not going to stop innovating for the benefit of humanity and inspiring the world through discovery. 22 will go down in the history books as one of the most accomplished years all of NASA's history and missions. The golden age of space exploration. So much to look forward to in 23. Climate missions that will tell us about how our Earth is changing. Game-changing aeronautics developments with the 59 and the X-57, and the selection of the first astronauts to go to the moon in more than 50 years. And there's a lot more coming. There was a philosopher, a historian, someone who had a great grasp of the future named Carl Sagan, a scientist. And he said, exploration is in our nature. We began as wanderers, and we are wanderers still. We have lingered long enough on the shores of the cosmic ocean. We are ready at last to set sail for the stars. We have set sail for the stars. Now we're going to reach out to the unreachable stars.
NASA researchers spend weeks, even months at a time, in remote locations around the world, collecting critical data about Earth's environment. Many studies are done from the air, using NASA's fleet of research aircraft. One such mission is Operation Icebridge, a multi-year study of polar ice conducted by the NASA Airborne Science Program. Icebridge sends NASA's P-3 flying laboratory to Greenland and Alaska in the spring to study changing ice conditions in the Arctic. A second aircraft, the NASA DC-8, flies from Punta Arenas in southern Chile in the fall to measure land and sea ice over Antarctica. It takes months of planning to execute a major international mission like Icebridge. Diplomatic clearances, configuring the aircraft with scientific instruments, and finding facilities that can support the people and the airplane itself are just some of the preparations needed for Icebridge to meet its mission requirements and goals.
To deploy to someplace like Chile, we plan a good 6 months before the mission to bring everything together so that once you arrive here, we're ready to execute missions on a daily basis.
Typically a mission director, a mission manager, program manager, we get called different names, will do the site surveys for the location, liaisoning with the government, of the host government to the host airport. That's the real legwork that's done prior, is coming out, make sure that they can house and feed us and take care of the people in the hotels. You name it. There's a lot of little tiny details that can't be overstated.
The biggest logistical challenge for the project as a whole is to set up all of the lab space and the facilities so that the scientists can process their data and make their decisions about which project.
Logistics is huge for something like this because we have to make sure we can all support the people in the field
as well as the aircraft. So we think a lot about aircraft spares and then little details about the support equipment for the airplane.
Usually on every deployment we're going somewhere, there's at least a group that goes out and scopes it out. A lot of it's done like while we're working other missions. And they will talk with the airfield, set up and tell them what we're going to be doing. And then as they're communicating back with us with what capabilities the airfield has to support us, that way we know what to ship.
For a deployment more than 6,000 miles away in the southern hemisphere, the maintenance crew needs to carry an extensive payload to maintain the DC-8 on site and keep the mission on schedule.
Yeah, we can put them right on the side there. Yeah,
More than 13,000 pounds of cargo are packed on the DC-8. Everything from spare tires, parts, and tools to basic comforts of home for the near-daily 11-hour research flights over Antarctica.
On a deployment like this, we bring the equipment with us, and we also ship a lot of other things by sea in a big container so that we can keep the airplane moving. It'll come back from a mission. If there's anything wrong that needs to be repaired before the next flight, we have the maintenance crew to support it during the night and get it ready for a mission the following day.
DC-8 flight operations team works around the clock to support Operation Icebridge, providing ground support for takeoffs and landings, operating the plane on research flights, and making sure sensitive science instruments stay powered up and heated overnight. The airfield is staffed 24 hours a day.
We have a makeup of about 28 people supporting the flight operations down here, and that consists of the pilots, flight engineers, navigators, mission directors, and then the maintenance crew that's split between mechanics and avionics technicians.
The maintenance team often works on tight deadlines to prepare the aircraft for its next deployment. Just 10 days after removing one set of science instruments from a previous mission,
the DC-8 is reconfigured for Icebridge. In 3 weeks' time, the plane is transferred